Alright, here we go. I am making an appearance, but I have to disappear because I can't handle the fact that I'm looking there, but the camera's there, and it's all over the map. So we're just gonna have to disappear me. Bye! Bye! Okay, time for the next unit. Now, this is a bit tricky because of the, I don't know, notation of it. So I'm going to fib to you for a little bit with this particular slide, and then we'll come back and we'll take a look at it again properly. So feel free to write this down or not, and I will give you the title in a minute, I promise. So the question is evaluate, and I hope that you know up to this point that if you get asked to evaluate, that means you are looking for a number answer. So we're looking for number answers along here. I'm just going to check again to see if there's any questions that require letters, and the answer is no. So I may do some scribbling off to the side here. Totally up to you whether you write this down or not. Please ask questions if you don't understand. So this question, or every question, numbers changing as I go, this question is asking, what is the power on the number 2 that gets us the 32? So we have to figure out 2 to the power of something is equal to 32. That's what this question is asking. And once we figure out the something, that will sit on this side of the equal sign. So we have to keep guessing and checking, and these are all supposed to be pretty answers. We have to keep guessing and checking until we get an answer. So I know that 2 to the exponent 5 is equal to 32, which means this answer is 5. Now we get to do it all again, only this time I'm asking you 3 to the power of something is equal to 27, and your job is to find the something. So I hope you can figure out that 3 to the power of 3 is equal to 27. So this little 3 upstairs, just like this little 5 exponent, is actually the answer. So this question is asking you, what is the exponent on 2 that gives you 32? What is the exponent on 3 that gives you 27? In this case, what is the power on 5 that gives us 625? So guess and check, guess and check, guess and check. Remember, they are looking for pretty answers, or I will look for pretty answers, and that answer would be 4. Now, there are some cases where there's some little trickster questions. So the first 3 questions weren't supposed to be tricky at all, except for maybe the guess and check part. So the next 3 questions are a bit tricky. So this question, same thing, different numbers, asking you 7 to the power of something equals 1, and your job is to find the something. I hope you remember from your grade 9 or 10 or 11 exponent rules that anything to the power of 0 is 1, so 7 to the power of 0 is 1, and that makes 0 the answer for this. Then we get to this question, also a bit of a trickster depending on your number skills, and all these questions might be asked at a school that does or does not use your calculator. So this question is saying 10 to the power of something is equal to 1 over 100. And our job is to figure out the something. So I hope you realize that 10 to the power of 2 is 100, but this isn't 100, this is 1 over 100, so that means you have to introduce the negative notation in the exponent. So this answer is negative 2. And this will come up repeatedly, as will this one, and questions like question F. So this is a square root sign. This is something that will also come up in calculus over and over and over again. This topic, as well as this particular type of example, is saying 2 to the power of something is equal to root 2. So what I hope you remember or learned in grade 11, and if you don't, you'll learn it now fairly well, ask questions if you need to, is there's a little 1 out here, or in here if you prefer, and this is a square root sign. Square root means what number times itself twice is 2. So there's a little implied or invisible 2 in here, and the way these numbers arrange themselves as exponents is the bottom number in the exponent goes in the hook. So that means the answer to this question is a half. As a little aside, if I give you the 5th root of x, for example, that means that as an exponent, that's x to the 1 over 5. If I give you the 4th root of q to the 3, and it doesn't matter if the 3 is inside the root or outside, that answer is bottom number went in the hook, so it's q to the 3 over 4. And we can continue this pattern for unlimited amounts of answers. Now I'm going to actually bring in what we're supposed to be doing, and that is not repeatedly using the word power. That's a bit bulky. And even then I'm saying that and I'm like, yeah, you know what, math can use whatever words it wants to. But the word it chooses is not power, it's the word logarithm. And the word logarithm is shortened to the button that you may see on your calculator, and that is the log button. So it's literally LOG. Now, you do have to wait because I'm talking about these tiny little numbers down here, and we will talk about them, so give me a sec to finish off some questions. And I hope you are seeing some questions that repeat themselves, and then boom, I've got some new guys. So, this question right here, evaluate the log base 2 of 32, which I will write down in a second, is exactly the same question as me asking you the power on 2 of 32, which is 5. So this answer is 5. So this question is the same as our previous question, and that is, what's the power on 3 that makes 27? And our answer was 3. Only now I'm being a little tricky in my language, my math language, and this is saying, what power on 3 is 27? And our answer is still 3. What power on 5 is equal to 625? And the answer is still 4. This one, what power on 7 is equal to 1? And our answer is still 0. What power on 10 is equal to 1 over 100? And we still have to use the fact that this is a fraction, so it's a negative, and 10 to the 2 is 100. So our answer here, even though you may not like this language, you're stuck with it, your answer here is negative 2. That part doesn't show up on the smartboard. So this next question, 2 to the power of something is equal to root 2. And just like before, I've just changed this part. There's a little 2 in the hook for square root and a little 1 on the outside, so this is 1/2, and my overall answer over here is 1/2. So this is like my scribbling side of the page if I'm trying to figure out things that don't appear in my head. So for example, maybe you just know this one and don't need the scribbling, but you need to scribble this one. So this is saying, what power on 6 is equal to the 4th root of 7776? So usually the numbers at a school that doesn't let you use your calculator, they don't get that high. I'm going to take out the calculator and see if I can figure out what the fourth root of 7,776 is, in case I can make this a little bit nicer. It means digging out my anything root button, and my anything root button looks like a bunch of things, but for me, it looks like this. Now, I have to figure out which order this calculator works in. So, this calculator, I'm going to do the fifth root of 32, which should give us 2, because of that first question we did. Okay, that's not it. So 32 goes under the hook. Second function, this button, put the number in the hook, and we get that. So for my example, it's 7776 under the hook. Second function, this button, specify that it's a 4 in the hook equals, okay, so that's not very nice. So we have to figure out, does 7776, is it made up of a bunch of 6s? So 6 to the exponent 3, too low. 6 to the exponent 4, too low. 6 to the exponent 5. Bingo! This is not an accident. So now I can say that this is 6 to the 5. I can put the hook over with the 4 back in, and then I can use this pattern to say bottom number went in the hook, other numbers here, so my overall answer is 5/4. And yes, you are expected to be able to figure that kind of stuff out by playing around. This is not able, none of these questions actually, A, B, C, D, E, F, G, none of these questions, oh, lied, E, work with your calculator log button. Neither does H, although I and J do, and I'll explain that in a second as well. Back to my promise, and I want to use question A as my example, not question B, which have repetitive numbers. The way you say this, among other ways, and I've got this written on a page elsewhere as well, this is log, comma, base 2 of 32 equals 5. And that is because the base of 2 to an exponent of 5 is equal to 32. So it's a base for the logarithm and it's a base for the exponent. So at least that word base is repetitive. Let's try a couple of last questions. Maybe you want to scribble off to the side. 3 to the exponent something is 1/81. So I know that 81 comes from 3 to the 4, but I don't have 81. I have 1/81. That means a flip happened, and if a flip happened, your exponent is negative. All right, now a little thing about logarithms. If there is no number down here, it is a 10. And the reason it's a 10 is because our number system is based on base 10. As in, when you count these numbers, for instance, this is the ones, the tens, the hundreds, the thousands, 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3 will give you 1, 10, 100, 1,000. So because this is our base 10 number system, as opposed to binary, which is base 2, in this case, that's a 10. So that's why it's chosen that way. So this question is asking you specifically for 10 to the something is equal to 100. Can you figure out that something? Hopefully you can do in your head that it's 2. That requires a lot of number skills. So if you aren't great with number skills in your head, then you have to make a decision before you pay for an education beyond high school, whether or not you need a school that lets you use a calculator or whether you need a school that doesn't let you use a calculator. So make some wise choices. Last question on this page, 10 to the something is equal to 1 over, this is 10,000. So you have to figure out how many tens makes 10,000. I believe it's 10 to the 4. See, my number skills are a little rusty. 10 to the 4 is 10,000, but it's 1 over 10,000. So we have that. So a reminder that if there's no number, it's a 10, and you don't have to write it in. You can if you like. So let's dig out the calculator for a second, because there's something I need to share with you. Most people will have this logarithm button. That is your log base 10 question. So that means if I punch this question in, I can just put in the 100, and I can hit the logarithm button, and it will plunk out a 2. Your calculator may work backwards in that you might have to do log 100 literally, and that's for display model calculators. The thing is, if I try that for even the top one, if we go back to that one, if I hit the log button on a 32, I don't get the right answer, at least not for a base 2, because this is how many tens it takes. So this is saying 10 to the exponent 1.5 blah 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 is equal to 32. We weren't focused on 10, we were focused on 2. So that's why you need to be really concerned about your calculator. Some of you will have to resort to using this button in a way that I'll show you in the future, not in this lesson. And some of you might have this crazy button where you get to change the base and you get to change what's called the operator, I think, and that is the thing that you're taking the logarithm of. So in this case 32, in this case 27. So this lets me mess with the base and it lets me mess with the operator. So I'm going to backtrack a little bit because I skipped over this slide number 2. I went directly from 1 to 3. So slide number 2 is from mathisfun.com, and I looked up algebra, logarithms. All of this is very important in calculus class, but I stole this stuff but referenced it, so I'm okay. So this is an introduction to logarithms, just in case you need words that were not mine. In its simplest form, a logarithm answers the question, how many of one number do we multiply to get another number? So how many 2's do we multiply to get 8? We need 3 2's to get 8. So that means the logarithm is 3. So we need 5 2's to get 32. That's why the logarithm answer is 5. Now I cut and pasted a little bit more. So we write this, the number of 2's we need to multiply to get 8 is 3. We write it like this, with or without the brackets around the operator. And they're saying that these two things are exactly the same. So if you're counting up the number, you put the number there, you put the answer there, and you put what you were trying to find in a bracket or not. So this is the base, like I said. So the logarithm of 8 with base 2 is 3. This is the one I prefer. Log base 2 of 8 is 3. Or the base 2 log of 8 is 3. So there's 3 ways that you can actually say this. And in case you are worried about any, or I guess interested in the history of math, John Napier, who sounds very French, was a Scottish mathematician, and he lived in 1550 to 1617, and he made up the word logarithm, and it's stuck all the way since, I guess that would be the 16th and 17th century. It's from the Greek word logos, which means proportion, ratio, or word, and arithmos, which means number. So together this makes ratio number. He picked a word that I don't think he should have picked, but I can't change every math book that you ever look at. I wish he would have picked something like power or exponent or something a little cleaner, I guess. Also know that logarithms happen in all sorts of places in, air quotes, real life. They happen in measuring earthquakes. They happen in measuring your hearing. So decibels are all based on logarithms. They are important in business. They are important in science, and you may deal with acids and bases. They're all based on logarithms. You might also see them in certain tests, as in when I was in high school, I worked in the respiratory therapy department as a volunteer at the hospital. That was a place that did all sorts of breathing tests, and any place that does breathing tests way back in the olden days before computers would spit out their breathing tests on logarithmic graph paper, and I will show you that after I take a little break, which I don't need now because I was talking. There are a few rules of logarithms, and I'm going to start going over them now before my little break to pull up the logarithmic graph paper, which is not quite as scary as complex number or polar coordinate graph paper, you know, that circle stuff that you may have seen before. So it's not quite as scary as that, but it's still pretty abnormal. I am hoping that you can't see me in this camera because it's gone and I'm waving. Hi, if you can. First law is law of powers. You need to know these laws. You need to know where they work and where they don't work. So we're going to go over them right now. So we're going to evaluate each of these questions by using the law of powers. So the law of powers, and all of this comes from the laws of exponents. The law of powers says that if you have an exponent, and I will move that circle in a second, but if you have an exponent and it's on something that you are taking the logarithm of, you are allowed to do this with it. You're allowed to take it from up here and plop it out front as multiplication. Now, why might that be handy? Well, the reason it might be handy is so that you can focus on this part of the question that you can actually pull off. As in, I can ask you, how many 2's does it take to make 64? And the answer for that is that there are 6 2's. So 2 to the power of 6 equals 64, which I would then have to multiply by the 3 that I stuck out front because of the law of powers, and that equals 18. So that's how the law of powers is useful. So the thing about an equal sign that I want to mention is I did this rule in the proper direction. Sometimes it works backwards. So I took the n that was on the x, whatever that number is, and I put it out front because my law lets me do it. If it is more useful, you can take an n that's out front and drag it up top. Those are rules that you have to be able to use interchangeably. So, let's see, I did make them movable. I'm just going to give myself a little bit of room, and we're going to look at this one. So, this question, evaluate. Hopefully you understand that you don't need the law of powers in this one because there is no power. In this one, there was a power. It was a power of 3. So this question is just asking you, how many 7's does it take to make 343? Now at this point, maybe your number skills are a little bit weak, and you may need to dig out your calculator to figure it out, or at least to trial and error, and that is okay, especially if you don't have this button. I would prefer you show some work. So maybe some, I'm going to call it fake works, because some of you might roll your eyes at this, but, oops, did not mean to hit that. So 7 to the exponent, not 2. I'm going to try 7 to the exponent 3. See what happens there. Hey, I got it. So that means that you could technically put in this line right here. And another thing is, if you notice here, that answer was 6. If you can match these two numbers, the base on the logarithm with the base for an exponent, your answer is 3, because you've found how many 7s make 343. So that's a line that even if you did this on your calculator, you could put that in as your work. Next question. So when I have, this situation, do you remember the rule? So I'm going to write down the other stuff temporarily, and yes, I bop between cursive log and printing log. Bases have to go downstairs, so if you're not a neat person, I have to mark you wrong if somehow the base for the logarithm rises to the top. So you need to keep it a little bit down below. Then I'm going to put this x down and remind you that the bottom number goes in the hook. So that means that as soon as you see a root sign, this number came from the bottom and the other number came from the top, and then I'm going to use this rule right here to say, oh, those guys match. There's my answer. Next question. Reminder again. There's a little 10 downstairs. So you can use and this is, everybody's got this button on their calculator. I'm not going to use my calculator because it's all the way down there. Too lazy for that. So you can put the 10 down if you want. And then I'm going to put this 10 down, and I have to figure out what the exponent is. Reminder, square root with an exponent 1. There you go. Matchy match. And there. And a question that we can't figure out today. So we will come back to questions like this. The only thing you can do for this question here is to write that. Oh, I lied. Oh my goodness, did you notice? I can do this on my calculator. I can evaluate. Now I'm going to impress some of you with my knowledge. 5 to the exponent -2 is 1 over 25. I'm going to put that in a bracket because it's a bit bulky. So on my calculator, I can do, show you this again, 1 divided by 25, and then I can hit the log button because everybody has a log base 10 button. So 1 divided by 25 equals that number. And then I have to hit the anything log button, so that's a little 10 down there. So everybody's got this baby. And we get that answer. So to 2 decimal places, I'm going to write -1.40. Now what that means is that if I wanted to use a base of 10 to create 1 over 25, I would have to use approximately an exponent of that. Exactly an exponent of this. Just so you know. Alright, so that's that rule. You got to get a grip on that one. We'll be using that repeatedly and for a purpose at some point. You will also use this in calculus class if you're taking calculus ever. So the next rule is called the law of multiplication. It is also called the law of addition. And then the law of division is also called the law of subtraction. Now the reason is, if I give you the same base, so the same base and I ask you to multiply with exponents, you actually add the exponents. And when I give you the same base and ask you to divide with exponents, you subtract. So the operations are linked because basically logarithms are anti-exponents. So I didn't write any bases down for any of these. That does not mean it only works for base 10. It just means that you could use a consistent base through the entire question. So we're going to bop between using the law of multiplication / addition or the law of division to answer these questions where, again, I'm asking you to evaluate. So come out with a number answer, please. Big eraser. And none of these guys you can use your calculator with, technically. I mean, you could do it here because it's got the base of 10, but we want to use these laws just as practice for the time being. So I'm going to move C and D out of the way a little bit. And we'll work on A and then work on B. I want these laws visible for the time being. All right, so you're supposed to notice that you've got two logarithms. You're supposed to notice that the logarithms have the same base, and you're supposed to notice that you're minusing in between. Another thing you're supposed to notice is there's no way to get 3 to be an 18. So if you did 3 to the 2, that's 9, and 3 to the 3 is 27. So you go soaring right by 18. So you can't do this without any decimals, and you likely can't do this without any decimals. So we get to use this rule. So this rule says if you've got a log of the same base twice, and you are subtracting, take the operators and divide them instead. And that's a legit rule. So I know I said my calculator was very far away. Total lie. 162 divided by 18 equals 9. So that bracket, I can scale it back a little bit. And this is something that you should be able to evaluate in your head. You should be able to see that this 3 means 3 to the something is 9, and I hope you can figure out that that something is 2, so our answer overall is 2. Yes, it is possible for you to go from here to there without the step in between, but it'd be nice to see this so that I can see your understanding of logarithms each time. The next question is the same but different. In this case, we've got log base 10. Doesn't matter what the base is, you still get to use these rules. And unfortunately, this time you're not subtracting, so you don't get to use this rule, but you are adding, so you get to scale two logarithms with the same base back to this. So you get to multiply the two operators. So multiplying means, see, there I go with the script again, and I'm too lazy to put down the 10. Dot for times. And a reminder that if you want to try to use your brain rather than your calculator in case you're at one of those schools, you could go over 1, multiply across the top, multiply across the bottom. So that turns out to be 200 divided by 2, which is 100. And at any time, like now for me, I would scribble down the 10, and then I would play the little guess and check, trial and error, to find out that 10 to the 2 replaces 100, matchy match, 2 again. So here is where I take a little break to rest my hand while you maybe take a look at these. Remember, you can pause whenever the heck you want to. But I'm going to take a little pause, find that graph paper, and come back to you. So here I go. See ya for a moment. Okay, so next question. Before I show you that logarithmic graph paper, we have to get through these two questions and then these ones here. I may need to use an extra sheet of paper for this one, or an extra sheet of smartboard notebook stuff. Anyway, so the first thing you need to recognize is whether or not the question has two logarithms or multiple logarithms with the same base, and this one does. Then you have to recognize whether it's an addition or subtraction question. This is a subtraction question, so what that means is that you get to use the law of subtraction, or if you prefer, the law of division. So it says that you can take subtraction and turn it into division. So that looks like this because I don't feel like using the old school division. I hope that you guys remember your exponent rules, which would make this question quite a bit easier instead of actually figuring out what 5 to the 14 is, or even 5 to the 6. But this is 14 minus 6, which is 8. And because you've got the old matchy match, your answer is 8. So, do you see a problem with question D that didn't exist in question A, B, or C? I see it very clearly, but then I have highly trained eyes. So in this question, both base 3, you get to use the rule. This question, both base invisible 10, you get to use the rules. The last question, both base 5, you get to use the rules. In this next question, I messed with you. You have to watch your math vision, and your math vision is supposed to pick up that the first half of the question has a logarithm base 7, where did that come from? And the second half of the question has a log base 2. So I'm going to pull this over because this is going to take us more work than the last few questions. Let's see if that worked. Okay, now I personally have a way that I like to do this question, and I'm going to do it off to the side. It means that I have a little bit of color coding coming. So I'm going to put the equal sign here, and I'm going to put the plus sign here, and off to the side, I'm going to take care of this part of the question separate from this part. So I'm going to start. But the first thing I'm going to do is not write down that part of the question. It is to take this 49 and give it an exponent, because it's 3, which is in the hook, came from the bottom, and the invisible 1 up here fits here. So the law of power says I don't have to look at that 1/3 up there. I can drag it downtown. And you can write this line if you want. And then figure out how many 7s make 49. So the answer is 2. And you matched. So this is 1/3 times 2, which is actually 2 over 1. So we can multiply across the top, multiply across the bottom, and this part of the question simplifies down to 2/3. Now this one. Dig out a different color. I'm going to do this one in blue. So log base 2 of 8 times the 4th root of 32. And there's a reason I wrote this down instead of making a shortcut here, and it's this 8. It's not really where I like it. So what I'm going to do is I'm going to use the law of multiplication backwards. I'm going to tear this apart. I'm going to say, okay, multiplication can get torn apart into addition of log of the same base of the two separate pieces. Now, I'm not going to write the 4th root of 32 here. Instead, I'm going to save myself a little bit of time and write 32 to the 1/4. 4 from the hook, 1 from the outside. Now I can do a little bit of playing. I'm going to do a little bit faster than the red one. So log 2, base 2, says turn 8 into a 2. So that's 2 to the 3. which means this part of the answer is 3. Plus, don't want to look at that 1/4 up there, drag it down there. And then I'm going to write 32 as 2 to the 5, because that's a really good replacement. So we end up with 1/4 multiplied by 5. And if you want, just so I don't go scrolling down here, we can put plus 3 plus 1/4 times 5 here. So now let's put this all together. If you're at a school that doesn't let you use a calculator, you cannot use your ABC button because that would be on a calculator. So first step is I'm going to multiply these together. 1 times 5 is 5 over 4 times invisible 1 is 4. I'm going to get a common denominator of 3, 1, 4, so that's 12. So I times this by 4 times this by 4. Times this 1 by 12 times 3 by 12. Times 4 by 3 times 5 by 3. So our answer is over 12 before we try to reduce it. So 36, 46, 51, 59. Let's try that again. 44, 54, 59. And this does not reduce, so we're done. So a question can be broken up into doable parts, and that's part of the skills of looking at math. I really like these questions because I'm good at playing at numbers. Yes, of course I am. I'm a math teacher. Let's look at our last 2 questions before I scare you with the graph paper. I also like these questions, even though these questions are not evaluate questions. They're quite a bit, I'm going to say, even simpler. To me, this is a bit of a puzzle. I'm asking you to write both of these, and probably many more, as a single logarithm. So in question A, this is not a single logarithm because I see 1, 2, 3 of them, all base 10, which means I can combine them. The deal is, I am not allowed to do any of these rules if there is a coefficient or a number in front. I'm allowed to put pieces back together, but I can't do it if there's a number in front. So for this question, this 2 and this 3 are not handy where they're sitting at all. So I can use the law of powers, where I can take the unhandy number and drag it up, because the law of powers works in both directions. So I'm going to write that as log base invisible 10 of m to the 2 minus log base invisible 10 of n to the 3 plus log base invisible 10 of p. So that piece didn't change. So I'm going to take this step by step. It can be done in one big swoop. Log base 10, and I am looking at these 2 pieces only to start with, and I've got a subtraction sign, so that means I can take the m to the 2 and divide it by the n to the 3. And I'm going to wrap it in a bracket because that's a bit bulky. And I still have to pay attention to the fact that I've got this. So we end up with log base invisible 10 of m to the 2 over n to the 3, and then addition changes to multiplication of p. And I'm going to do one more line, put that over 1, so that my fraction isn't so spread out. Log base invisible 10 of m squared p, all crushed together because we're multiplying across the top, over n to the 3. And there is this long stringy mess written as a single logarithm, meaning that the logarithm base 10 that was written 3 times is now only written once. So we're going to try that again with this question, the last one, only this one doesn't have any numbers. And I need you to know that all these rules, this one, these two, even the patterning, are actually quite difficult until you start practicing enough to make them less difficult. So, this question, let's use blue. Again, invisible 10 base all the way along the length of the question, so I get to use my rules. I'm going to focus on this first of all, even though I could do it in all one big mess. But I'm going to take log base invisible 10. This is addition. So I'm going to do x times y in a bracket because that's a bit bulky, minus, do you see the problem there? Toss it up, and then we can put it finally together. It's subtract. It's all log base 10. So now it's division. Brackets for the bulkiness. All right, so that's it. And I believe that this is actually correct. So I am going to put this on full screen to show you that even though I've got 3 to 6, 9, 10, don't do L, 11, 14, 15, 16, don't do B. When you get to 9 and 16 and eventually 17, there is a document on the Google site that lets you look at the answers for those. I actually have them here written. There's 9 for this. There's 16 for this, and for the future there's 17. So you can take a little picture of this, you can look on the Google site, there's a whole lot of options for you, but I thought I'd at least explain that in case this actually matches your homework. So that is the beginning of logs. We are going on to use logs for various reasons over the next few lessons, including a couple of, air quotes, real life situations. So there you go. And, oh, the graph paper. Almost forgot. So this int math site I think is fabulous. It's British. We've looked at it before for trig identities and I think the biorhythms stuff. So when I look at this stuff, I now believe that when I was in the respiratory therapy department, I didn't use logarithmic graph paper. I used semi-logarithmic graph paper. And the thing about semi-logarithmic graph paper is that one of the axes is normal and the other one is logarithmic. So one of the axes does its normal scaling, as in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, etc. As opposed to logarithmic graph paper, or semi, where this, I don't know, for lack of a better phrase, escalates quickly. So first one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then you go up by 10, so 20, 30, 40, 50, 60, 70, 80, 90, 100. And then you'd go up by hundreds, so it'd be 200, 300, 400, 500, 600, 700, 800, 900, 1,000. And then you'd go up by 1,000. So it's logarithmic because you're going by powers of 10. So there's an example graph of semi-logarithmic. So here's your 1, 2, 3s. They've decided to use fractions here, and then we go up there. Logarithmic graph paper, which I think is implied in the fact that that was just semi-logarithmic, and I don't know why this isn't moving. I'm going to use my mouse. I give up. So logarithmic graph, ooh, there's traffic charts, an example of semi-logarithmic graph examples. Financial charts, when you're talking about large sums of money over time. Then we get into log. So this is logarithmic graph paper, meaning you're using logarithmic scales on the bottom, or I guess on one of the axes, and using it on the other. So it's kind of messy. It looks terrible. There's another example, a little bit blown up. It lets you graph really, really large numbers and really, really small numbers without butchering your scale and smushing stuff in or super having to spread it out. So that's why it's handy. And of course, they don't have any examples of that. Oh, nope. There. So you can look the stuff up if you like. We won't be graphing using logarithmic graph paper, but I did want you to know that it exists. I'm going to take a guess that it is also used in lie detector tests, but that is just strictly a guess. So I did talk about a bunch of stuff today that wasn't necessarily related, and that's why this lesson is so long. I will be back with another one momentarily, but you can look at it anytime.